Good afternoon, everyone. Thank you for joining us for this webinar. This is the Automated Space System Architecture Design. My name is Josh Poley, and with me is our VP of Engineering, Kevin Flood. Kevin started off his career at GE Aerospace in Valley Forge. He's had over 30 years experience on this topic. He used to work in space hardware for optical and communication design. He was on the Space Defense Initiative and from the System Engineering and Integration team. He's worked test and evaluation systems for antenna and radar measurement systems. And now he leads our engineering team, who is the team that is responsible for applying our software for all sorts of applications and across many organizations all around the world. Also here today is Jens Ramrath. He is a senior systems engineer. Jens is here to help with any of the questions. And if you've ever called in support and had a hard technical question, there's a good chance you've crossed paths with Jens before. With that, I'll turn it over to our speakers. Kevin?
All right, thanks, Josh, and thanks everybody for joining us today. We have a pretty straightforward agenda. I'll spend a slide or two talking about some of the industry background that's kind of leading us to the conclusions that we're going to present to you today. And then we'll jump into a reference case study that allows us to highlight some of the important factors that we've learned over the years getting involved in trade studies like this for space systems to draw out some of the important factors that we think we'd like to share with you as you look at executing these kinds of trades for yourself. And we'll save some time at the end for questions and wrap up. So by way of background, I expect that most people on the line are familiar with AGI to some degree and know that we are a commercial software product company. In that role, we spend a fair amount of time looking at other technology companies who are successful in their areas of endeavor, and software companies in particular. And we, like a lot of folks, have been very impressed with a lot of the internet software companies, and impressed in particular with their ability to quickly innovate and bring new products and services to market, but even more so with their agility in how they respond to their customers when their customers apply those technologies and services in ways that they didn't expect when those products and services were first launched. So to a large extent, we're being asked to bring that same type of agility to the space world. And I think if you look at the quote here from General Hyten, the commander of U.S. Strategic Command, kind of highlights the need for doing that, where he says, if we're not going faster than the threat, then it's wrong. And it highlights the fact that our space systems are being employed and applied for missions and applications that they weren't originally considered for. Now, fundamentally, the space domain is very different from the internet domain in that we have to contend with initial investments, capital expenses, and cycle times that prevent us from employing the same techniques that we see on the internet side. So from an industry perspective, the overall mandate is for us to accelerate the entire life cycle and bring new capabilities and services, or adapt those capabilities and services to market a lot more quickly. So the way that we're going to do that is to learn quickly by launching those new products and services, but to do it virtually, to launch those through simulation, and then use trade study analysis to explore the new technologies and those new architectures to learn rapidly how we can make our systems more resilient and more adaptable. And that's going to be the focus of what we're talking about today. And what we'll really drill into are some of the key attributes of the tools and processes that allow us to bring that speed and that agility into this learning process. And to do so, clearly we'll be using some of our products as examples for doing that, but we'll be using products that exist today. One of the things that we won't touch on in today's presentation, but is an important factor, is that all the tools that we're talking about today, while available right now and capable of addressing today's problems, are all adaptable as the processes that we're using in our engineering organizations evolve to include model-based engineering and model-based system engineering throughout the entire life cycle. So that's an important element that underpins a lot of the things that we're talking about. And we'll have future webinars that go into that in more detail. What we will touch on is the ability for these same tools to operate similarly in all operational domains, not just space, and to ensure that we can incorporate participation by engineering members from all of the engineering disciplines so that these frameworks and these methods of learning and accelerating the design process can be inclusive over the entire engineering organization. So here's the approach that we're going to take for today. We're going to use a reference example that we can use as a framework to highlight some of the procedures and processes that we're talking about. And we'll first break that into a very high-level analysis. So we'll make a lot of system engineering level assumptions. We'll run a series of trade studies and use these tools and processes to draw out some of the important learnings. And after that, we'll branch off, take a couple of specific points out of that process and evaluate them in more detail using more detailed models to illustrate how we can incorporate these models in conjunction with each other to validate system engineering assumptions, to create branch points for the next level of iterative analysis, and to even begin making the transition over to the system engineering process and the requirements definition. So let's set the framework for the discussion. We'll use an illustrative reference example so that we can refer to something specific as we illustrate these points. So the case we've chosen is a space system to perform persistent surveillance. And to provide a little bit richer storyline, we'll look at two areas of interest. We'll look at persistent surveillance covering the entire globe, and then we'll select one high priority area to look at in a more concentrated fashion. And we'll look at a number of different measures of effectiveness as we evaluate the quality of the systems that we're looking at in our trade study. And in addition to that, we'll include cost as a factor, as that's an important element of any trade study consideration. So in our practice of being involved with the delivery of commercial software products and being involved in system architecture studies over time, we found that these are some of the key elements that are really responsible for achieving rapid acceleration of those processes. And so as we go through this, we're going to highlight each of these factors and share with you some of the things that we've learned over the years as we've delivered these products to customers and observed their successes. And we'll start out at the very beginning of this process with rapid model building. So from a modeling perspective, here's where we want to end up. This is a graphical illustration of a complex constellation that consists of cooperative interaction between satellites in two different orbit regimes. Each of the satellites has a primary mission sensor, and we're going to be looking, as I mentioned, at two areas of interest, the global area and a specific target of higher priority. So for the sake of illustration, we've chosen the United States to be that target area. We've distributed about 1,500 points throughout those so that we can measure the effectiveness for our persistent surveillance mission. And we'll be using a simulation time of 24 hours as we go through the trade study. And I mentioned on the previous slide that we have 8 measures of effectiveness in addition to the cost. So that's going to be the framework within which we're going to be looking at the performance here. And right now we're focused on the ability to rapidly construct the models in order that we can conduct these trades efficiently and learn as much as possible about the driving factors that support resiliency and adaptability. So in the model building process, essentially what we need to do is we need to create 2 reference orbits that are going to be the basis for our 2 sub-constellations. We need to define the sensor characteristics, the geometry, and the resolution. And then we have to define the model that represents the mission. So the geographic distribution of the mission objectives and then the specific measures of effectiveness. So let's go through the creation of each of those model elements. And I'm going to point out some of the things that are ultimately responsible for achieving rapid model building, since we're going to want to do this process over and over in an iterative fashion. So right from the gate, one of the things that we've learned is that wherever possible, it's always good to start with something that already exists. So if we're looking at the orbit models, for example, we see here an illustration of an access to a database that allows us to pull in the orbit definitions for existing assets that we can then use as points of departure to do our trade studies. And the same thing applies to other models that we've created in the past. We like to ensure that we can save those, make those discoverable, and make those reusable as rapid starting points. Now, when that's not possible, one of the things that we've learned is at the beginning of these processes, it's absolutely essential to create easy, efficient ways to create that starting point. So what you see here is a wizard for defining some of these orbits. And you can see in the illustration that it allows you to choose from all of the different standard canonical orbit types to select the parameters and, again, create a starting point that you can use as the model for the point of departure when you do your trade studies. Now, whether you use existing models or you create your own from a wizard or some other fashion, there are a couple of attributes that are absolutely indispensable as we go through these automated trades. And one of the critical ones is that these models are data-driven. So we don't want to have to go back in and rewrite scripts or recode and recompile the models. So what you see here is a properties panel representing all of the key attributes and the parameters of variation that we're going to care about as we define the orbits and we define the constellations. And all of these parameters are exposed to automation APIs using standards-based technologies. And you'll see in a moment as we get into the trade study execution why that's an important factor. So those are some of the important attributes as we set up the models for our satellites and constellations. Now we need to do the same sort of thing for our mission definition. As I mentioned, our mission definition consists of the geographic distribution or the geographic constraints for the mission and the measures of performance. So defining the geographic distribution, we utilize tools that effectively allow us to sample in an efficient way and a controlled distribution across our area of interest, whether that's global or whether that's defined by some geographic boundary as we have with our United States high priority area of interest. And we can define that resolution such that it's effective but not overly constraining for the kinds of simulations that we want to run. So those are going to be the geographic distribution models that we use in our reference trade study today, but those aren't the only ones of interest for this type of trade study. So let me go through a couple of other types just to be a little bit more exhaustive here. So in addition to uniform sampling, we may have a very tightly specified list of specific target points for this kind of application, and we want to be able to apply the same efficient model creation and the same types of analytical calculations that we're going to show as we go through this process. And you can absolutely do that using this same type of platform. And these need not be limited to Earth-based targets. So we can use the same type of distribution or uniform sampling in well-defined distributions on land, in the air, or even in space. So again, with the focus on being able to rapidly create models that we can use as points of departure for trade studies, these are some of the techniques that we've found to be critical in defining the mission models and the geographic distribution for those. And for those distributions, we then want to apply measures of effectiveness. So in the almost 30 years of our creating these kinds of tools, we've realized a number of the key attributes and the key performance parameters that we like to make available right out of the box, things like number of accesses. And in addition, we recognize that in the early parts of architecture trades, we want to be able to make some logical system engineering assumptions. So for parameters like system response time, that can be actually modeled in detail by creating more higher fidelity models and including that level of detail in the overall trade. We can make a lot of good system engineering assumptions out of the gate to simplify the model to allow us to get through a lot more sample points earlier on and help us to identify the key architecture drivers. And this is one of those examples. So response time takes into account some of the time constraints for commanding, the response time for the vehicle, the communication times. And by making some logical estimates for those components, we can create a high-level model for that level of mission effectiveness. And when we get into the detailed model discussion later in this presentation, we'll show how we can come back and revisit some of these assumptions. In addition to system-level requirements, we might want to include some of the performance characteristics for the main mission. So in this case, we'll care about the resolution for the sensors that we're looking at. We can include parameters like ground sample distance. And just to be comprehensive here, we do recognize that at some point in time, we're going to want to include some sort of custom figure of merit. So while we don't use it explicitly in this example, we're showing here how you can incorporate an external library. In this case, it would be another form of image resolution figure of merit when that is constructed using a standards-based technology like .NET. So in summary, for the rapid model building, we looked at what is required to create physics-based models for the orbit definitions that we can use as points of departure in the trade study, and create the mission models that will be our measures of effectiveness as we evaluate the models. For us, it took about 4 hours to create all that. Now, to be clear, it took Jens about 4 hours to create all that. And admittedly, Jens is a very sharp aerospace engineer, and he's been doing this for a long time. But nonetheless, the reality is that there is easy, accessible training available that in the span of about 3 days, a trained engineer in engineering disciplines could become at least functional, if not proficient, in these same tools, such that the time required to create this kind of model should be measured in hours and not measured in days or weeks. So those are some of the key takeaways regarding efficient model building. Now we'd like to move on, since we have our model constructed, and actually set up the trade study. And that's going to take advantage of the second key factor, which is ensuring that the platform that we're using has easy and accessible automation and integration interfaces. So what we're going to be doing here is, for the model that we just constructed, selecting the specific control parameters that are going to be the parameters of variation during our trade study, identify the measures of mission performance that we'll use to evaluate the performance of the system, and when necessary, program other models. So in our case, the only thing that we need to program is the cost model. And then an important step is then to define the trade space. We're going to look at doing that in two different ways. So there are a lot of standard tools that are used throughout our industry, MATLAB being one of the most prevalent ones. So we actually conducted this trade twice, once using MATLAB and once using our own set of tools. So this shows an interface in MATLAB that highlights some of the important aspects of having standards compliant automation APIs. So the key properties that we showed in those models in the previous slide are now accessible through this IntelliSense interface, such that skilled engineers who are familiar with MATLAB, like Jens, can quickly gain access to those parameters and use the MATLAB programming language to set up the automation and the trade studies, and then use some of the powerful graphical tools inside of MATLAB to analyze those results. Now, more appealing in some cases would be to set up those same types of trades, but to do so without requiring any scripting. So what you see here is an interface that directly connects to those control parameters and those figures of merit definition that allows somebody using this interface to simply drag and drop those parameters in to define the trade space, the control parameters and the response parameters. And what's more important is that when they do so, they can actually define the bounds of variation such that another engineer who might be skilled in a different discipline who wants to use this trade study can do so confidently without fear that they're going to violate some bounds that don't make sense for a parameter of variation that is outside her or his area of expertise. And one last factor that's absolutely critical is having easy access to define very efficient sampling data points. So the next topic we're going to talk about is the need for scalability, as these kinds of trade studies can become computationally very large. But one of the hedges against that is to use smart sampling algorithms that avoids full parametric variation over all possible ranges of factors. So that's what you see here, is the ability to select a number of data points that you want to use as the entire scope of your trade study, and have a smart algorithm figure out how to distribute the variation or parameters over that trade space. So again, just as reference, it took Jens about 4 hours to create both of these. And again, there's a lot of training available, so the ability to get up to speed is really quite efficient. And in the span of essentially one workday, we were able to set up the entire model that we're going to use as a point of departure and define the trade study. So now we're going to move on to executing the trade study, and the focus of the emphasis here will be the need to ensure that the tools that are being used can be scalable. So just to set the reference a little bit, let's look at the primary control parameters that we're considering here, and there are a total of essentially 9 for the kind of study that we're doing. And admittedly, this is a pared down study just to illustrate some points, so this set could be a lot bigger than 9. But even for 9 parameters, if we look at the number of discrete simulations that we're going to want to run in order to evaluate this trade space, if we consider just applying 2 different values for each of those parameters and looking over all combinations, the result is that we're going to run in excess of 500 discrete simulations. And if we only bump that number of parameter values from 2 to 3, that number balloons to over 60,000 individual simulations. So not only does this reemphasize the need to have smart sampling algorithms, but it also illustrates how the size of the trade study analysis can become large pretty quickly. And again, this is just looking at one constellation and the parameters of variation for it. If we add 2 constellations or a third constellation, you can see how these grow exponentially. Just to reemphasize the size of the problem here, each one of these simulations is a simulation over a full 24-hour period, and that could largely be bigger than that in many cases in order to properly evaluate the performance. And for each of those simulations over that 24-hour period, we're looking at somewhere on the order of 100,000 discrete access calculations for all the vehicles in our constellation to all the sample points throughout our areas of interest. So that's over 100,000 access calculations over however many discrete simulations. And if we add in our measures of mission performance and look at the number of calculations overall, we're looking at 500,000 to 1 million calculations per simulation. So again, this is just to sort of set the scope for how big the scale of these problems can be. So our takeaways from being involved in these, again, for almost 30 years at this point, is that there are 3 critical elements. The first is that it's fundamental to start with an efficient computational engine, an engine that is purpose designed to solve this kind of problem, to efficiently propagate orbits by the definitions as we vary the parameters that create those, to be able to manage layered geometric transformations that account for orbital motion, planetary motion, and the combination of platforms and payloads as we evaluate constrained accesses and do so over a distributed region. With that fundamental engine in place, we then need to add scalability so that we can take advantage of computing resources. So for the reference case that we ran here, we conducted a 500 simulation run on essentially a standard issue engineering laptop. And that took about 16 hours, taking advantage of the 4 cores that are available in that processor. Now, there will be cases where there's just no getting around the need to evaluate many, many trades and many, many simulation instances. And in that case, we need to make sure that the technologies that we're talking about are adaptable for distributed computing and high-performance computing systems. And our customers and others that have been involved with us have demonstrated the ability to scale the calculations for acceleration 1,000-fold and more using the technologies that we're talking about today. So again, our takeaway from conducting these, being involved in these kind of experiments with our customers over the years, is that those 3 elements, an efficient computational engine, scalability, and then adaptability to high-performance computing systems are critical for us to move rapidly through that trade study analysis and identify resilient and adaptable systems. Now, once we've done all that and we've generated all the answer, we get to the so what point. So the whole idea behind this is to rapidly deploy these systems in virtual simulation mode and then understand what the key drivers are and the key risk areas are as we evaluate their adaptability and the resiliency. So in order to make that happen, we want to take advantage of tools that allow us to gain insight into the results that are produced so that we can learn from that process and figure out how to take the next logical step. So what we're talking about in this phase is collecting and organizing all of the data that comes out of those multiple simulation runs, applying techniques to allow the analysis of those multidimensional responses so that we can identify the performance drivers and the risk areas, and then figure out what we should do next. There are a lot of techniques that are available, and we could probably fill up a whole webinar, if not a whole day of training, going through graphical analysis techniques. So I'm going to revert to some simple techniques that I usually fall back to that allow me to highlight a couple of important factors for looking at these multidimensional data sets. So one of the things that I like to do is to start with a simple graph and to pick out the two parameters that are of greatest interest to me. So for the case that we ran, we identified the U.S. region of interest as our high priority region. So I'm going to look at the average system response time for that U.S. region on the vertical axis. I'm going to look at my system cost along the x-axis. So you can see the distribution of the points on this graph for those two parameters that are of most interest to me. So one of the values of using this graphical approach is that you can pretty quickly see through the distribution the emergence of what's referred to as the Pareto frontier. And that's essentially the line that connects all of the optimal solutions for these two parameters. As you go off the Pareto frontier, your solution is worse. It's either less performant or more expensive or both. And then as you move along the Pareto frontier, you're essentially trading one parameter for another. So what we're looking for here is kind of the knee in that curve, which you can kind of see from the curve that's overlaid here. So that's a great tool and technique to identify where logical breakpoints are in this multidimensional data. The only problem is that we're really only looking at 2 dimensions when we do this kind of analysis. So we can take advantage of some other graphical techniques to overlay some other dimensions. So in this case, we take advantage of color to represent the average response time for our global area of interest, and we look at the size of the distributed points to represent the worst case system response time in our U.S. area of coverage. Fortunately, in this case, they all kind of line up very well, but that's not always the case. Now, there are a lot more parameters that we might care about. So another important technique to include in looking at the multidimensional data is the ability to actively filter the data sets for other parameters. So if the parameters we're looking at are the 2 that we care about the most, we can then go through and apply filters against the other resulting parameters to take out data points that don't satisfy fundamental threshold conditions. And once we've done that, we have that same Pareto frontier that we care about. We can now interactively choose on our graphical tools the points of interest to us, and we can look at all of the different control settings that resulted or that produced that result, and we can, in an automated way, load those back into our simulation platform and create a new simulation, which essentially becomes a seed for us to do the next level of iteration and the next level of learning as we go through this process of discovering the key drivers for resiliency and adaptability. So in executing this process, it took us about a day to come up with these results that we're presenting here. And the reality is, it took us almost no time at all to collect and organize the data since it's all in one tool set. And the creation of the graphs, again, was pretty straightforward. Most of the time here is spent reorganizing the data and doing the human analysis of the data to try to draw out the different important factors. So having tools that provide that flexibility and interactivity was a key element in order for us to go through this quickly. So essentially what we've done for this high-level simulation is in the span of about 3 business days, go through the model building, the definition of the trade study, the execution of the trade study, and the analysis of the data to produce the results that we've just illustrated right here. And what we'd like to do at this point is to branch out from here and go back and revisit some of those system-level engineering assumptions that we made by incorporating higher fidelity tools and layering that on to the system-level design. So in this second part of the presentation, what we're looking at is the extension of the analysis process that is going to allow us to pull in some more detailed models, and we're going to want to do that for a variety of reasons. So in the first phase of our analysis and system trade study, we made a number of simplifying assumptions. So for the specific point that we pulled out by selection in the analysis in the last slide that we showed, we're going to want to go back and validate that some of those simplifying assumptions made sense and that we weren't oversimplifying. Additionally, we want to incorporate models of higher fidelity so that we can take that point design and now do trades that incorporate those more detailed platform and payload considerations. And ultimately, we're going to want to make the transition over into the system engineering process and the requirements development. So incorporating the models at this point makes sense from a life cycle perspective. So what we'll do at this point is look at a number of specific cases and types of models that we can put on top of those architecture models. And the thing I'd like to emphasize is that all of these models subscribe to the same fundamental characteristics that I discussed when I went through the rapid model building description, which is all of these models can be built in the span of a few hours by a trained engineer who's been trained in the tools that we're using. All of the models are data-driven, subscribe to open APIs, and so are adaptable to the automation trade processes that we just showed. So let's go through each of these, and this is going to be pretty quick and pretty high level, but hopefully it will be illustrative. So a couple of the assumptions that we made early on is that for our persistent surveillance analysis, it was adequate for us to simply model our sensors and our sensor satellite combination with a geometrical projection for field of regard. We didn't worry too much about specific tasking and the combination of targets that might be concentrated in different areas. And even though we looked at the collaboration between two different subconstellations, we didn't explicitly define what the cooperative rules might be for how those systems might work together. So considering that those considerations might have an impact, we can go back at this point and construct a more detailed model. And here's an example just for the sake of discussion and illustration on how this might work. So assume, for example, that the higher altitude regime component of our subsystem, of our constellation, has sensors like radars or maybe IR sensors that, once they identify a target of interest, may want to queue a follow-up acquisition from a higher resolution optical sensor in our low Earth orbit subconstellation. And for the sake of argument here, let's assume that we'd want that collection, that follow-up collection, to happen within 15 minutes of the first observation. And we'd like that to happen under certain conditions. So we'd want the sun elevation to be within a certain range of the target of interest, and we'd want the collection geometry for that optical sensor to be within some limited range of that sun illumination angle. So again, we're defining this just to illustrate how we might incorporate a model for this mission level definition into the platform that we've been discussing here. And you can see in the picture described above a target of interest, which is the Statue of Liberty. You can see the geometrical representation for the sun illumination angle and the acceptance range for the viewing perspective that we want for the follow-up collection. And what you can see on the bottom component of the Gantt chart are all the time relationships that exist for that definition. So on the top line are the collection opportunities for our high altitude sensors. The next line represents the acceptable windows for the follow-up collection. The third line are all of the opportunities in an unconstrained manner for the optical sensor in the low Earth orbit. And then on the bottom line are all of the combinations that satisfy our mission definition. So one of the things we see here is that we may have overly simplified our mission definition in the initial trade study, because there are a lot of collection opportunities from our high altitude queuing sensors that can't be acceptably followed up on by our low altitude sensors. So that illustrates the reason for wanting to go back and construct a more detailed model like this. But in the spirit of the need to rapidly build models, one of the key elements of this sort of model definition is that in many cases, mission unique definitions are composed through a combination of directional constraints, spatial considerations, time considerations, and calculation of measures of effectiveness. So again, in that same spirit, what we want to do is to have a model creation mechanism that allows you to rapidly create those models in a span of hours, have all of those models be data-driven, and have all those data elements accessible to automation interfaces so that they can be included in trade studies. So what we could do in this case is take that definition that we just illustrated on the prior slide, we could plug that back into the distributed calculation and rerun some of those trade studies that we did in the first case with this more explicit definition for the mission performance parameters. One of the other simplifying assumptions early on in our high-level system trade study was that comms were fully available and that there were no resource constraints that would in any way impede the execution of the missions that we were looking at. So one of the things we might want to do is to look at the accessibility to ground stations for telemetry and commanding communications and actually run a schedule that is able to pull out any resource conflict and resource constraints. And that's what we've done here. So you can see in the Gantt chart that actually with a limited number of ground stations distributed around the globe, there are a number of contact opportunities that would be missed simply because of capacity limitations for the ground stations. So where we would likely want to go from here is to reevaluate some of the other elements of the architecture that can facilitate the deconfliction of some of these resource constraints, whether that's adding more ground stations or being able to use these resources in a more efficient manner. And in order to do that, what we want to incorporate into this trade space is a schedule distribution mechanism, a schedule distribution model, which can be rule-based or probably more importantly, can be designed to create optimal scheduling and allocation of resources based on whatever our definition is for our figures of merit, for our highest priority mission requirements. And that's what we're illustrating here is the mechanism by which you can define what those priorities are for your resource constraints and how you can run this scheduling model against this architecture design to evaluate the need to either add more resources or to be able to redistribute allocation of responsibilities in a more efficient manner to deconflict those resource constraints. And in that same spirit with regard to communications access, we can consider other architectural changes that might alleviate some of those resource constraints, like incorporating intersatellite communications. And again, we can do that at a system level using geometric considerations in a simplified manner. But as we look at moving into the next phase of the engineering process, we may want to incorporate models that account for the critical design components for the antennas and terminals that we'd likely use to achieve these intersatellite communications, and make sure that we have models that properly represent the channel characteristics as we evaluate those performance elements. So what you see here is a model building panel that allows you to design your satellite crosslink antennas, in this case a phased array. And again, it emphasizes the fact that these models are data-driven and these data parameters are available as parameters of variation in the trade study. We mentioned that we made some simplifying assumptions early on with regard to system response time, but now as we start layering in more levels of performance fidelity and we look at some actual collection scenarios, we'll need to start bringing in vehicle dynamics to figure out what those response times actually are. So here's an interface that shows how we can define some of the important subsystems of the vehicle and the attitude control system in particular as we play out some of those specific examples. And since we're building out the vehicle model and incorporating key subsystems, we can include other subsystems in this modeling process, like the power management system and the thermal management system as well. And when we do that, we can define some representative target collection sequences, as you see illustrated here. So you can see the sensor footprints as the satellites go through their targeting sequences that were defined using the scheduling model. The attitude control system handles the pointing, and you can see on the right-hand side the panels that represent the performance of the power subsystem and the actual performance of some of the attitude control elements. Now, in the same vein, we may want to extend some of the simplifying assumptions about our sensor performance from simple geometric assumptions that include ground sample distance resolution and simple lighting constraints. And one of the things that might motivate us to do this is our evaluation of system resiliency and adaptability. So, for example, if we're looking at a ground surveillance system and we want to evaluate its ability to be reapplied for a space surveillance application, we can do that by incorporating a physics-based model and the phenomenology models for the atmospheric physics and actually execute that kind of scenario, which is what you see being performed here. So in this case, we're looking at a ground-based optical sensor being redirected at another low Earth orbiting satellite. And what you can see here is the actual scene rendering for the image that would be produced. You can go into each pixel in that scene and look at the performance characteristics. So if we wanted to extend this model even further and look at the system implications, we could set triggering thresholds for this kind of sensor performance and integrate that into the overall mission performance analysis. With regard to the constellation, as we look at lifetime considerations, we've glossed over the need to perform station keeping and the fuel implications that that would entail. And that's another level of fidelity that we can layer into the architecture study. So an example of that would be for our low Earth orbit satellites in a circular orbit pattern, being able to maintain some level of relative orbit for each of the satellites in each ring of the constellation. So what we've constructed here is a model that incorporates auto sequences to keep this particular satellite with it at about a 30-degree latitude separation from a reference orbit, and to do so such that it never exceeds a plus or minus 1 degree bound. And so you can see here the simulation results that are played out over a 90-degree period. You can see where each of the station-keeping maneuvers are performed. And this could be done for the entire architecture. And for each of the satellites, we can then draw out from this model what the fuel consumption is and verify that the assumptions that we made for the fuel budget for this mission would be adequate. Once we start getting close to the final definitions of our systems, we'll want to look at other lifetime considerations, and that means being able to bring in models for the space environment, to look at radiation particle dose, to look at the thermal loads that are going to be placed on our system, and the magnetic field effects. So those can all be incorporated in the same way as the other models that we just discussed. And finally, we haven't really given much consideration to the ground system design other than to talk about possible constraints from a communication perspective. But a couple other factors may be important for consideration, like ensuring that we have adequate observability to ensure space safety of flight, or for precision mapping missions, potentially, we may want to ensure that the orbit prediction accuracy is adequate. So other models that would be appropriate to help us flesh this design element out would be the ability to model actual sensor performance, the sensor accuracies, the number of observations and frequency of observations, and the number of different ground stations. And another place where this type of analysis becomes important is as we consider the build-out and the phasing and the adaptability of systems over time. So the initial deployment of the system may not require type, orbit accuracy, or orbit prediction accuracy, but if we wanted to have the flexibility to adapt it to a higher accuracy mission in the future, if we know ahead of time that we can do that by adding more ground stations or upgrading the accuracy of our sensors, that's important to know before we make the investment in the space system. So I know that was a very quick survey analysis. Hopefully that brought out some of the key points about how it is important to be able to layer on models of higher fidelity onto our high-level architecture model to validate our fundamental system engineering assumptions, to set ourselves up to do more trades and to make that transition into the engineering process. So in summary, the motivation behind this entire discussion was looking at the role of modeling and simulation for accelerating our ability to bring space capabilities to bear, and specifically to do so in the architecture design phase. And what we want to emphasize is the ability to learn quickly through modeling and simulation, through rapid model building, efficient execution of trade studies, scalability, insightful analytical tools, and then the ability to layer in models of different fidelity so that we can shrink timelines that had normally been measured in days and weeks to hours, and weeks and months to days. So for all of our analyses, we took advantage of SDK, which is a systems toolkit, which is that purpose-built, efficient computational engine that I mentioned in the scalability section. This development has been underway for a number of years and provides a unifying framework that operates at a high level, supports scalability, and gives you the flexibility to integrate models of different fidelity levels internally to SDK or your own external models through standards-based automation interfaces. The specific products that we used for the high-level trade study were SDK Professional, SDK SAP Pro, the analysis workbench for some of the vector definitions, SDK Coverage for evaluating the performance figures of merit, and SDK Analyzer to define and execute the automated trade study and do the engineering analysis. We also used MATLAB, which we did in parallel to execute the trade study. So we did the trade study using two different automation formats. And while we didn't actually execute any external code, we did demonstrate the ability to pull external libraries defined in standard-based technologies like .NET into this same framework. For the specialized analysis, we reviewed the SDK Analysis Workbench, which allowed us to define the more detailed mission performance requirements, SDK Scheduler for the contact planning, SDK Communications for the cross-link design, SDK Solus for the vehicle design and analysis, SDK EOIR for the sensor analysis, SDK Astrogator for the station keeping and fuel budgeting, SDK Seat for the environmental analysis, and ODTK, and in particular OD Simulator for the analysis of the ground station and the OD simulated performance. So at this point, I'd like to pause and take a breath and open the floor up for any questions.
Yeah, thanks, Kevin. Yeah, we got a couple questions here. And I'll read them out, and you guys can just decide who answers them. And I'm going to paraphrase this, so apologize if I change it a little bit. But what type of training should I take to do this type of analysis? And do I need to get certified?
All right, I think I'll start off, and then Jens can chime in if appropriate. I would start with each level of the analysis, or each level of training. So our training is broken into three phases. The SDK level 1, which is the basic introduction to the SDK framework. Level 2, which essentially gives you all of the ability to run all the trade studies that we did in the first part. And the level 2 training is a 3-day training. And then the level 3 trainings are a series of specialized trainings that bring you into the tools that we spoke about in the second half of the program. So I would start at the beginning and go through that entire process. I think certification is always a good idea to validate the fact that you understood the material adequately.
Thanks, Kevin. And another question here is, does this work for interplanetary studies?
Yeah, everything you can do on the Earth, you can generally do, anywhere else, or on Mars or Moon, or any of the other central bodies. We have basically everything in our solar system you can load into SDK. If there's something we don't have, you can just create your own custom planet object or comet or whatever it is you happen to care about and load that in SDK, and then you could do the exact same analysis, around any other central body.
Thanks, Jens. Okay, another question here. What's the difference between CubeSats versus traditional satellites for these tools?
For us, it really doesn't matter. It's just, the performance, you have different area to drag ratios, so your orbit will be slightly different. You may not have the power on your transmitter that you have on a CubeSat that your big satellite has. But it's really, for us, it's just a number you change, and then, the actual analysis will be different, but, you just use your actual values. So for SDK, it really doesn't matter if you have a small CubeSat with a low power antenna, or have a huge satellite with a lot of power. So the analysis is really the same.
All right, thanks, Jens. Okay, another question is, how do I get the software of everything you listed to test it out?
You can go to our website and you can download the software, and for the software that's not included in the download, you'll have the ability to submit your request for a demonstration license for that. We provide some on-demand licenses so you can try the software out. And if you're going to do that, I definitely recommend that you do it in conjunction with the training. We offer live virtual trainings. We offer in-classroom instructor-led trainings, but you can also do self-paced trainings because all of our trainings are recorded and available online, and it helps to go through the tool while you're going through the training to understand the different controls that you have and model building features that you have inside of SDK.
Yeah, and I'll just add to that is there's also the home use license. If you're going to be going through the certification processes, on the same website Kevin's talking about, you can get an extended license for home for education purposes, and I believe it's 6 months still. Yeah. So you have to have the software for 6 months, so you can take the training and get certified at your own pace. Thank you very much, Kevin and Jens, for answering that. That's it for today, folks. Stay tuned for future webinars. You can stay in the loop with those if you go to our blog site. If you want to talk to an engineer, you can email info@agi.com. And like we've said a few times here, go to agi.com/training and begin your own training, self-guided, sign up for a class, whatever works for you. And like I said, any of you that ask questions individually, we'll follow up with you separately, so we will get your questions addressed. Thanks, everybody. See you again soon.